9 a.m. So let's continue. And what? In the previous lecture, actually yesterday, we started using Gauss's law, basically now as experts, to analyze properties of conductors, right? And of course, I haven't covered all properties. So first, I will discuss those which we actually analyzed in the lecture, and then I will add a few additional properties. But you know what? Before we dive into conductors, and that's the major part of today's class, let me go back to the problem which we solved in the previous class. It's a 2450, right? Why? Because we solved this problem in the recitation class using the volume charge density, right? You remember what was the problem? We had some infinitely long charged cylinder, and we needed to find the electric field outside and inside, right? We solved the problem, but again, using volume charge density. But in your homework, there will be similar problem with linear charge density. So let me connect those two densities so that it would be easier for you, right? Okay. Well, first of all, let me write, of course, lambda. It's linear charge density. Linear charge density. And you remember, what are the units of linear charge density? How can we find linear charge density? For example, you have this rod, right? Let's assume. And let's say you know the total charge. Let's say Q. So how can you find linear charge density? You need to take the total charge Q, uniformly distributed, and divided it by the length, total length of the rod over which that charge is distributed. It's a linear charge density. So, of course, as a result, what will be the units? Units are going to be coulombs charge divided by meters. These are units of lambda. But the volume charge density, which we used in this problem, rho volume charge density. So how can we find that? For the same rod, the same object, right? Again, we will take the total charge, but now we will divide by the volume of the whole cylinder. Here we divided it by the length to get linear charge density. Again, it's still the same object. So you can introduce two different charge densities, right? Okay, so in this case, as I said, you need to take total charge and divide that by the total volume of the cylinder. So of course, as a result, units are going to be coulombs divided by meters to the power of 3. So now, how can we connect lambda and rho? Right? Okay, question mark. So I'm going to use part A of this problem, part A, in order to show how can we connect these two densities, right? So let's use part A. And let me remind you what we had in the part A. We had that our charged cylinder, right? So we had pluses, right? So charged cylinder. And then we had a Gaussian surface, which was, of course, outside, right? Because we were finding electric field outside. That was our Gaussian surface. And of course, as a result, where is the enclosed charge? Enclosed charge was here, right? So that was our Q enclosed in that part A. So now let's write this Q enclosed using linear charge density and then volume charge density. And of course, since we're talking about the same charge, of course we can equate those two expressions. Okay, so let me write that down. So using linear charge density, Q enclosed will be Again, if you don't know, do you have to multiply or what to do in order to get a charge? Look at the units. We want to use now linear charge density, and we want to get charge. Units of charge must be at the end. So in order to get units of charge, coulombs, of course, this lambda must be multiplied by the length, right? By the length. And of course, this length of this Gaussian surface, you remember, was L. L capital we introduced. So in order to find that charge using linear charge density, we need to take lambda and multiply by that L. So it will be lambda times L, right? So we used linear charge density. Now, volume charge density, we've done it in the class, in the previous class. So now, of course, again, if you're not confident what to do with that volume charge density, look at the units. We need to get units, coulombs divided by meters to the power of 3. And we want to get at the end coulombs. So of course, this rho must be multiplied by the volume so that these meters to the power of 3 would disappear. So it will be rho n times the volume of that this bluish highlighted cylinder where Q enclosed is. So it's a pi r squared times L. R, remember, it's the radius of the cylinder. R is the capital R capital is the radius of the cylinder. So now just comparing these two things, right? Of course, you can see L gets cancelled, and you get the relationship between these two densities, right? So we can write that rho equals lambda divided by pi r squared. Or you can solve it for lambda if you need, right? Okay, so that's what I wanted to discuss, right, related to the previous class. And now, now we can go back to our conductors, right? Okay, so that's related to the previous. So now, even using the results which we derived in the previous class, you can get results for the homework in terms of lambda. And of course, this can be used for part A or part B, right? We're talking in the same charge distribution. So back to conductors. Again, as I said, now we are experts in Gauss's law, and we decided to use that law to analyze properties of conductors. And what we found. First of all, we compared dielectric material and conducting material, right? And the major difference between them is conducting material has conductors, metals, have tons of free electrons. Because you remember what is material? It's a basically crystalline structure, right? Bunch of atoms, right? And between them there's a gigantic spaces, empty spaces. And in metals, that space is filled with free electrons. So they have freedom and democracy, right? So they are free to go anywhere they want, right? If you apply an electric field, right, of course, as a result, they will start drifting in a certain direction, giving us current. But in the dielectrics, that empty space between those atoms in the crystalline structure, it's empty. So all electrons basically are imprisoned by the nuclei. As a result, you can apply the potential difference or electric field in a dielectric material, but there is no current because all electrons are tightly bound to nuclei. That's why dielectrics are insulating materials, basically, right? Okay, so first, as I said, so electrons, conductors have tons of free electrons, right? Then, then we introduced the idea of electrostatic equilibrium, right? So what happens to a piece of metal in the electrostatic equilibrium? Electric field inside must be zero. When electric field inside of the conductor is zero, we can say that that conductor reaches a state of electrostatic equilibrium. Like we discussed, if you take, for example, some piece of metal, expose it to the electric field. And of course, inside of this piece of metal, first electrons will start running like crazy. In order to achieve what? in order to make electric field zero. Otherwise, they will never stop running. They will keep running and running because they feel electric field. They will experience electric force. So their goal is to make electric field inside of the conductor zero. At that point, they can relax. They can stop running because they don't feel electric force. They can, as I told you, they can reside, get settled, buy a house, and live happily ever after, right? So in the electrostatic equilibrium, of course, you have to wait for a short period of time. Electric field inside is zero, inside of the conductor is zero, and electrons stop running. So at that moment, we can say, yeah, our conductor is in the state of electrostatic equilibrium. Right. Then, yeah, so now I can add, so over here, electric field is zero. Right. Then, next one, what if we charge this piece of a metal, piece of a conductor? So now it has excess charge. And we analyze that situation in order to answer the question, where can that excess charge reside? Right? Where can it be? And we proved that inside of the conductor, it's impossible for excess charge to exist. Again, excess charge, it doesn't mean that inside of the conductor, it's impossible for any charges to exist. No, no, no. Inside of the conductor, there are again still tons of electrons and tons of positive charges, but their total charge inside must be zero. We're talking about excess charge. Excess charge can be only on the exterior surface, in a case like this. It can be, if you charge it positively or negatively, right, every time, that excess charge will be on the exterior surface. In simple words, if you dump some, for example, electrons at this point, of course, they're all negative. They all repel each other because you remember, like charges repel. And of course, they will try to run as far from each other as possible. And of course, what are the farthest points? The surface. So any excess charge, let's assume it's positively charged, on the surface. Then, next, what about the electric field outside of the conductor? Inside of the conductor, it's zero. We know. Basically, you see all the time we're talking about charge, electric field, charge, electric field, inside, outside. Right? Basically, that's the extent of of what we're discussing. So now electric field outside, again, we discussed it in the lecture. Electric field outside of the conductor all the time is perpendicular to the surface. It's again, in the electrostatic equilibrium. Right? Before it reaches electrostatic equilibrium, it's a mass in the conductor. We don't want to dive into that mass. Every time we will assume that we wait for, I don't know, maybe a nanosecond, maybe picosecond, maybe microsecond, who knows? It depends on the conditions, right? And when it reaches electrostatic equilibrium, and then of course we can start stating all these conditions. So electric field outside of the conductor is perpendicular. So that's electric field outside. Okay, and then of course we did not derive, but I just told you and showed it on the slides. So that's the magnitude. That's how you can find magnitude of this electric field outside of the conductor. In one of your homework problem, you'll have to use that. It's quite. And again, eta is a surface charge density. Why surface? Because the charge is on the surface, right over here. Excess charge can be only on the surface. So of course we can talk about surface charge density. Okay, and now a few additional properties which we didn't discuss in the lecture. First one, now let's make this situation, make this system more complicated, because now we know everything about the electric field and charge. Nothing else we can add to this particular picture unless we can make our picture more complicated, the system more complicated. How? Let's drill a void, a hole inside of the conductor. And of course, that hole, that void, doesn't have a connection to the outside world. So it's completely isolated inside of the conductor. Right? So charged metal with a hole. So that's what we added now on top of that, right? Okay, let me draw a new picture. So let's say that's my conductor, again, steel piece of metal. And now, how much of space I need? Okay, let's assume that this is my hole. So the conductor is over here. Right, so that's my conductor, that's the whole void. Again, there is no connection with the outside world. And again, let's assume it's charged. You see? I wrote charged metal with a hole. And now, of course, logical question. Over here, when we had only one surface, we proved that any excess charge can reside only on the exterior surface. But now we have two types of surfaces, exterior and interior. And of course, now absolutely logical question. Is it possible for this excess charge to reside on the interior surface? Absolutely logical question, right? Let me write it. Which way I stated it. Are there any there any excess charge charge on the interior surface? Okay, and let's prove it. Let's basically not prove, kind of derive it. And you should be able to guess which law I am planning to use now. Gauss's law, right? We've just derived it, not derived, sorry, wrong statement. We just discussed it in the previous lecture, right? In the previous recitation classes. Now we can just use it, right? So, Gauss's law. Let's apply it. E dot dA equals to Q enclosed over epsilon naught. And of course, you remember the first step? We must pick a Gaussian surface. You remember, any Gaussian any surface, any closed surface can be used as a Gaussian surface, right? It's a universal law, no restrictions. So at this moment, my soul desires to pick a Gaussian surface just, I don't know how to say, below or above this interior surface. Just above interior surface. Let me use that word, right? So that's my Gaussian surface. You see, over here for this case, that's my Gaussian surface, just below or above. I still don't know what to say, how to say it correctly, right? And look, what's the value of this integral? Basically, this is the flux through that Gaussian surface. You should, at this point, you should be able to tell me immediately what's the value of this flux, right? It's 0, because this conductor is in the electrostatic equilibrium, and the electric field inside of the conductor must be 0. And since our surface is still inside of the conductor, so electric field is 0. So this flux is 0, right? Okay, let me remind you. So, of course, electric field inside is 0. Since the electric field inside is 0, so this is 0. So the whole integral is 0. And Q enclosed as a result 0. As a result, we can write that Q enclosed equals 0. So there is only one place where a charge can be. It's just on this interior surface. That's what is inside of the Gaussian surface, and we showed that charge there. It's impossible for charges to be on the interior surface. So impossible. All right. So are there any charges? No. There are no. Impossible. So it's impossible for any excess charge to be on the interior surface under these conditions, if you have an empty void, right? Okay, again, there the question, are there any excess charges? Any excess charge on the interior? No, it's impossible. Right? Okay, so now, before I move to the next kind of property, now let's extend these results in terms of applications. Look, can you guess what will be the electric field inside of this void? I guess you shouldn't have any hesitations, right? Yeah, of course, I see, right? Since electric field there is zero, there are no any charges on the interior surface. Of course, the electric field inside of the conductor will be also zero. How can we use this result? Very important application follows from this immediately. At some point, I thought even about using something like this. It is used a lot. Okay, guys, imagine you have some piece of equipment in your setup, in your experiment, in your device, right, which is sensitive to some electromagnetic fields, maybe to cell phone signals, right, or maybe whatever, right? Tons of signals now in our space, right? And let's say your piece of equipment is sensitive, right? It picks up, as a result, it distorts your result or distorts your image, right? There are tons of situations, right? Audio signal, right? So what you do, if you shove your piece of equipment in that hole, it will be free from influences from the outside world, from those electric fields unwanted. Basically, we're talking about Faraday's cage, screening, shielding of the equipment. I remember in my last year of my PhD, right, I had an experiment, and after a few down conversions of the signal, my signal was around 100 megahertz, and I hated our school's radio station because there's a antenna on the foxhole, right? And I remember still about sort of, I think, on the spectrum analyzer, every time I saw that strong signal, 92.5, I think, I don't remember megahertz, that frequency. Damn it, I hated it, right? Because it, it influenced my results. So, but of course, yeah, my advisor first suggested let's build a kind of Faraday's cage around the whole optical table. But then, of course, with filters, we managed to filter that out. So that's my emotions towards the folks. I mean, the UML radio station. Right? So Faraday's cage. Of course, you don't have to very often create some solid material. Sometimes cage is enough, right? Sort of like a made of mesh, right? Sometimes you can use maybe some foil, right? Or you can use some conductive paint of the box. It's enough, right? Of course, everything must be properly calculated. So yeah, but this results as tremendous applications, right? Uh, okay, let me write. Okay, so E equals 0 inside, and let me write it can be used to, which way I wrote to, shield sensitive equipment. Sensitive equipment. Okay, Faraday's cage. Of course, these results you can see in the slides, right, which I posted. Then, all right, maybe I should write Faraday's cage because it's a Faraday cage, right? Faraday's cage. So now, what else we can add? How else can we make this system more complicated? What if we dump a charge in the hole? So again, we'll have a conductor with the void, and let's dump a charge inside of the hole. Right? So now let's position Q in the hole. So now let me draw the picture. So that's my conductor. That's the hole, right? So that's the material of the conductor, right? And the charge inside of the hole, let me use quite different color. So let's say this is my, let's assume it's positive Q. And again, the same question. It's a charged piece of metal. And the same question, where is it possible to have a charge, or what will be the value of the charge on the inner surface and on the outer surface, interior surface and exterior surface? The same question about the charge. And so we have charged conductor. Did I say what? Okay, yeah, charge conductor, and the same question. Maybe I can move. Okay, show that the same question can be used over here. I just don't want to rewrite it one more time, right? The same question. And in order to answer that question, you should be able to guess which law I'm planning to use. Again, the same damn Gauss's law, right? Again, the same Gauss's law, right? So integral of the closed surface E dot dA equals to Q enclosed over epsilon naught. And again, you have an option to pick any surface, Gaussian surface you want. Again, my soul wants to choose the Gaussian surface just above or below this interior surface. The same like here. All right, so this will be my Gaussian surface. Okay, thanks. um, okay, so now the same question. I mean, now of course you should be able to give me the value of this flux, electric flux. Again, this conductor is in electrostatic equilibrium. Electric field inside of the conductor is zero. So this electric field is zero. So as a result, the whole integral is zero. Again, the electric flux is zero. As a result, we can tell that Q enclosed is zero. So of course, Q enclosed is zero. If the left-hand side is zero, then of course the right-hand side must be equal to zero. But now the situation is more complicated. Over there, we did not have any charges inside. But now we see that there is a positive charge in the hole. And in order to make the total charge within the Gaussian surface zero, there must be some negative charge minus Q somewhere. And of course, we have only one place for that negative charge to exist, between that Gaussian surface and the interior surface. So basically we can say that that negative charge must be somehow distributed along the interior surface. Of course, distribution will be complicated. It depends on the shape of the void. It depends where you position the charge, but we can say for sure that the total amount of charge on the interior surface will be equal in the absolute value to Q, but with the opposite sign, minus Q there must be. Right? So now I can write something like this, so that Q enclosed equals to Q and then plus Q on the inner surface. All right, because there are only two charges, this positive and some charge on the interior surface. So of course this is zero, as we just showed. And of course, as a result, charge on the inner surface must be equal to minus Q. Again, total charge somehow distributed along the interior surface. So as a result, Q inner surface, difficult to write here, equals to minus Q. Okay, so we're going to use that in the problems, right? In simple words, electrons inside of the conductor, they see this positive charge. Of course, they feel attracted, and of course, they will run towards that positive charge, right? And of course, they cannot reach it. Of course, they will all end up on that interior surface. Right. Okay, so that's what we needed, and now let's start discussing problems. Okay, I don't need this sphere. Okay, I will erase this. Yeah, there's no option. New markers usually leave lots of darks. So, problem 35. 24, 35. Questions similar to this, quite often I give among multiple choice questions on the exam. So, It's something like this. Let's assume that we have a conductor which is charged. So we have a conductor, basically a piece of metal, and the total charge of that conductor, it's charged. Q total, TOT, is negative 50 nanocoulombs. So it's negatively charged. But this conductor is with a hole. Then, okay, maybe I will draw first. Which way you draw it? This way. Right. So let's say this is our conductor piece of metal. And as I said, there is a hole. So let's say this is a void. So this is metal. Right. And as I said, this conductor is charged with the total charge minus 50. Okay, let me show that. It's here inside of the conductor. But at the same time, there is a charge it's positive. Yeah, positive, so I can use red. So there is a charge over here. I will label it as Q sub H. H because it's inside of the hole, right? Q sub H, and the value of the charge is 100 nanocoulombs. Right. So that's the situation, and the question is simple. We need to answer the question how much of charge is going to be on the interior surface and the total amount of charge on the exterior surface. So in part A, all right, so let's say, so we need to answer the question, what's the amount of charge on the inner surface? And then part B, on the outer surface of the piece of metal. Right. Okay, the first question you can answer without even justifications, right? You should be able to answer it immediately, right? It's basically what we derived over here. Of course, if you want, you can repeat these steps again, right? So pick the Gaussian surface just above this inner surface. Flux is 0, Q enclosed is 0, and since there is a positive charge inside of the hole, there must be negative charge of the same value on the inner surface in order to make Q enclosed 0, right? So you should be able to write the answer for the first question immediately, right? So we can write Q inner, okay, I will drop surface, right, equals to minus Q hole, and it equals to minus 100 nanocoulombs. So we just proved. Just proved it. Oops. Part B. Okay, guys, if you need more explanations, okay, tell me, but I think we just discussed it and I just applied it directly. Right. So now, so that is Q inner. Okay, maybe I should, what I do this, show that this Q inner is on this surface, right? So on that interior surface. Maybe I can even show minuses. So minus, 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 minus. Then outer surface. Now Q on the outer or exterior surface. Okay, I will use outer. Now we need to use a different law. I'm planning at least, right? Yeah, usually if I ask students, right, can you sort of suggest which law can be used now in order to get the amount of charge on the outer surface? Not everyone sees that. Okay, now I'm going to, not the Gauss's law. No, not the Gauss's law. All right, I'm planning to use conservation of charge inside of the conductor. We assume that we're working with rubber gloves, that there are no any leakage of charge through air. So basically it means that this total amount of charge which we dumped in the conductor must be in the conductor all the time, no matter what. So this Q total, because that's what we gave to this conductor. And that's what it has, nothing else, right? So then we know that. Then where now, remember these properties, where can this total charge be? Of course, it will be somehow distributed somewhere, right? We know that it's impossible to have any excess charge inside of the conductor. It's impossible, physically impossible, right? God created nature this way, right? We show that it's impossible. Only charge can be only on surfaces, right? Inside of the conductor, it's impossible to have any excess charge. So we have only two surfaces, inner surface and outer surface. So this Q total can be only on the inner and outer surfaces. Somehow, some of them, we already know what's the amount of charge on the inner surface, right? Okay, so now let me write. So now we're going to use conservation of charge, and I'll emphasize inside of the conducting material. This charge QH, it's not inside of the material. Yeah, physically it's inside of that body, right? But it's not inside of the conducting material. I just want to count the total amount of charge inside of the metal. Basically over this, in this highlighted region. The conservation of charge, and I will emphasize inside this metal. Emphasize. And let me write, QH is not in that metal. Because that's the most common place for confusion. Because okay, up over here, we apply Gauss's law. And every time we counted all the charges physically present inside of the Gaussian surface. But that's for Gauss's law. That's how Gauss's law treats charges. Conservation of charge and Gauss's law has nothing in common. Those are apples and oranges. We just need to remember that, okay, Gauss's law treats charges this way, conservation of charge that way, right? So that must be clear. So now we're not using Gauss's law, we're just counting charges inside of the conducting material. And QH is not part of the conducting material. It's inside of the void, in that vacuum. Okay, so I can write, so Q total equals Q on inner surface plus Q on outer surface. Because charges, any excess charges can be only on surfaces. Inside of the metal, impossible. Just showed it over there. So Q total, we know. Q inner we just found, and that's our unknown. So just one equation, one unknown, we just need to solve for Q outer. All right, it's basically, it's like I don't know, 1.5 minute problem to solve. But of course, first we need to discuss it properly. So as a result, Q outer will be equal Q total minus Q on the inner surface. And Q on the inner surface we just found. Right, so let me show that this goes there. Okay, so now let me write. So Q total is minus 50 nanocoulombs. Then minus from the formula, and there is another minus from the value of the charge. Minus 100 nanocoulombs. So as a result, I'm getting 50 nanocoulombs. Right? Let me check. Yeah. So plus 50 nanocoulombs. And it makes sense. Add charge on the outer surface over there will be 50 nanocoulombs. On the inner surface, minus 100 nanocoulombs. So if you add them up, you will end up with minus 50 nanocoulombs, the total charge, right? Explanation is very simple, right? So when electrons saw this positive charge inside of the hole, of course, they started running towards the inner surface to make electric field inside of the conductor zero, right? And of course, as a result, they left behind significant amount of positive charge. although the total conductor was negatively charged, but because these electrons left behind significant amount of positive charges on the outer surface, so as a result, outer surface becomes positively charged. Right? Simple explanations. Yeah, I wanted to draw this pluses. Plus, 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 and plus. Right? So that's, let me show that it's here. As I said, quite often a problem of this type I give among multiple choice questions on the first midterm exam, or maybe sometimes in the final exam. And again, it's just in terms of mathematics, there's no mathematics basically, right? Just adding numbers. In terms of physics, it allows to probe, right? Understanding of properties of your understanding of properties of conductor. Okay, so now next one I probably wouldn't be able to finish. We'll see, because this one is lengthier. All right. Okay, I need to start erasing that. We need these properties probably. Cool, awesome. All right. This blue marker is absolutely new. As a result, leaves so much of residue. So 36, 24, 36, and I think it's also in your homework, this problem. I just wanted you to repeat by yourself. It's a hollow metal sphere is given, charged. Okay, let me draw it. How much of space I need? All right, so let's say this is outer surface. Yeah, and then there is a hole. Okay, they're supposed to be concentric, and they are more or less concentric, right? So metal is here. Okay, radii. Let's say this is, I think, A. Yeah, this is A. This is B. Right. Then this conductor, again, it's let me emphasize, it's a conductor. Hollow conductor. And again, every time we're going to assume it's in the electrostatic equilibrium. So we waited for some time, it's there. Then it's what is given A, B, right? So those radii, and the total charge of the conductor plus 2q. So let me show that this conductor is charged with plus 2q charge. Then, to have more fun, let's add here charge plus q capital at the center of the void. So that's the situation. Yeah, and we need to find electric field everywhere. So we need to find electric field. So find electric field everywhere. Okay, what do I mean by everywhere? So there are three obviously regions: in the void, in the conductor, and outside of the whole structure. So this will be first region, second region, and the third one. Okay, so again, conductor is charged. Again, nothing happens to that charge stays there. Of course, some of the charge will be on the inner surface, maybe some of the charge will be on the outer surface. Right now, I don't want to discuss that. First, I want to find electric fields. And guess which law am I planning to use? Now, Gauss's law. Now Gauss's law, right? Because we have nice spherical symmetry, it will be the best approach to this problem, right? So let's start with region number 1, right? So Gauss's law, integral over the closed surface, E dot dA equals to Q enclosed over epsilon naught. And again, first step, you need to pick the Gaussian surface. Without that, we wouldn't be able to move any further. So Gaussian surface, of course, must be in the region in which you're interested, right? In the region number 1 over here. And of course, again, you can pick any surface, and you will never be wrong. But we need to solve the problem, and of course, the best surface is another sphere. So that will be our Gaussian surface. Of course, concentric with this structure. So Gaussian surface, and maybe I will show it like this. So that's our Gaussian surface of some arbitrary radius r small, like we've done in the lecture discussing spherical symmetry. Now basically we have to repeat one more time, right? Okay. Probably I'm not going to draw pictures. I will just of course electric field will be still radial. Area vector will be still towards the outside perpendicular, right? So it's radial. So it will be, let me write, at least in the first part, dA equals, right? So first, since electric field is parallel to dA, exactly the same steps like we've done in the lectures. Maybe I will draw. So area vector, for example, over here. So that's dA. And of course, electric field will be still radial because of this spherical symmetry. So that's electric field, and that's why I wrote that. And of course, as a result, my dot product gives me just the product of two magnitudes. Right? Again, cosine of the angle is 0 degrees, right? So theta is 0 degrees, cosine of 0 is 1. As a result, dot product gives us product of magnitudes. Okay, so now, second step, symmetry. It doesn't matter where you are on that Gaussian surface, electric field strength must be the same because of the symmetry, because distribution of charges at any point will be exactly the same for any point. So E equals constant on the Gaussian surface. Again, now I'm not spending as much time as I spent in the lecture, a couple of lectures ago, justifying all these steps. Now I expect that you remember those, right? So if it's a constant, we can extract electric field from the sign of the integral. As a result, we're getting E and integral of the closed surface of dA. Of course, integration over that sphere of radius r small. So, of course, it will be equal to E times 4 pi r squared. So that's the flux. Again, I just repeated steps from the lecture. And it must be equal to Q enclosed over epsilon naught. And what's the value of the Q enclosed in this case? You should be able to see it immediately, right? So there's only one charge, that point charge plus Q inside of the Gaussian surface, nothing else, right? So in this case, Q enclosed equals to plus Q, right? So as a result, these can be solved for E. And I will add subscript 1 as a function of r. 1, it means in the first region, right? So it will be a Q divided by 4 pi epsilon naught, and then r squared in the denominator. Q divided by 4 pi epsilon naught n times r squared. So that's for region number 1 when r is less or equal than a capital. Okay, now before we go, right, what will be the electric field in the region 2? Who can tell me? I see one answer. Exactly, 2 answers, right? Yeah, that's what I see. The rest are right. You can only express your opinion through voices. Exactly. The second region, it's a conductor in the electrostatic equilibrium. All the time, electric field there must be zero. Electrons will keep running and they will never stop until they will make that electric field zero. Otherwise, they would feel electric force and will be pushed, right? So, electric field in the second region is zero in the conductor. Right. Okay. But again, so now be careful because this is true because we're discussing conductors. What in the lecture, when we analyze similar situation, in that case, we had just a dielectric material charged, or maybe some sphere stuffed with charges, but those were not conductors. So read the problem. If it says charged dielectric material with a uniform distribution of charges, of course, we cannot say that the electric field is zero because that's not a conductor. It's only correct if you have a conductor. So be careful because lots of mistakes are done there. Okay, so there is the third region. I will send you my notes, but let me just tell you what will be the Q enclosed because this part will be exactly the same for the third region. You just pick a Gaussian surface over here. What will be Q enclosed? Oh, nice cat. All right, so what will be Q enclosed? Q enclosed will consist for the third region out of this plus Q and then plus 2Q. Of course, we don't know. Some of this charge will be on maybe on the inner surface. Some of the charge will be on the outer surface. But Gauss's law doesn't care where the charge is. If the charge is inside of the Gaussian surface, just count it in, and we know that the total charge is plus 2Q. So for the region 3, the Q enclosed will be Q plus 2Q plus 3Q. So that will be the charge for the region 3. Okay, so you should be able to do it by yourself, the region 3, and I will send you my notes. I will scan them and send to you, right, so that you can check. This problem will be in your homework. Okay, guys, if you have questions, you can ask. Otherwise, I will see you tomorrow, right, Thursday.